and Phononic crystals received the prestigious Mediated Prize for the best thesis. And following his PhD, Matt became the first Kavli Nanoscience Institute Prize postdoctoral fellow at Caltech, before moving on to Sandia National Lab as a Harry S. Truman Fellow in National Security Science and Engineering. During his time at Sandia, Matt founded and led the MEMS-enabled quantum systems group. And now, as Sandia's first distinguished faculty joint appointee, he's splitting his time between Sandia and the University of Arizona, where he recently established the quantum nano, how do we pronounce this? Nano-photonics.
Yeah, I don't know, it's terrible. It's like, X equals NRT, like phonons and photons.
Great.
Phonics or something.
Okay, I'll let you explain that.
Yeah.
Looking forward to.
Thank you. I guess we don't usually say it out loud, so.
The silent X.
Could I join the Zoom or just I guess I'll just plug in? This is HDMI or? Yeah. Also, sort of note to self, like when somebody asks you for a bio for a talk, like consider the difference between you just sort of like getting it pasted on the walls on papers, or like the person hosting you have to read the whole thing out loud and you'll write it differently. So anyway, but yeah, thanks for the invitation today. The talk that I'm not going to give, though, based on the lab tours I got this morning, I think, this would have been a very relevant talk to give. So essentially my group has invented some ways of doing quantum photonic integrated circuits using all CMOS fabrication. So this is making quantum photonic integrated circuits on 8-inch wafers and CMOS foundries that also make CMOS electronics. We've done a lot of cool things like integrating diamond with vacancy centers for having integrated quantum resource state generators on chip. And we have a lot of unique ways of kind of controlling those degrees of freedom of the spins and the optical transitions. We're doing a lot of collaborations these days, doing things like making specific photonic integrated circuits for controlling neutral atom quantum computers. Lots of interesting things to talk about, but my talk today is going to involve none of that. Instead, I'm going to talk today kind of exclusively about, well, 35% of the talk will be about phonons. So this is some work that my group's been doing now for about the last 8 years. We started off just sort of doing these classical electron-phonon devices that I'll spend the first part of the talk on, and then in the last couple of years, we've sort of moved on to looking at some quantum interactions between electrons and phonons in these devices, and I'll tell you all about it. So let's start off with the motivation that kind of got us into the field. So if you were to break open your phone, okay, you have a few antennas, and those antennas are kind of multiplexed to a bunch of different radio bands, right? So you have radio bands, you have multiple different 5G bands, you have 4G bands, you even have 3G bands in your phone, even if it's a super fancy phone, because there's only 3G voice. You have Wi-Fi bands and Bluetooth bands, right? So all these things are basically just different frequency bands where you're transmitting information, right, back and forth. You send some out, you get some back. And those frequency bands, basically take modulated information, and they need to either encode it onto a radio wave, send it out, or decode it off the radio wave to, basically put it on to the digital processor, right? So there's this chip, there's this essentially system that sits between the antenna and your baseband processor, your computer, right? It does all of the encoding and decoding of information, right? So you have digital information in the computer. Here you have fully encoded radio frequency information coming in and going out. And in between, you have to basically do all these things to take that information off the radio waves and make it digital again, or put it onto a radio wave, so essentially modulate the radio waves. And so the component that you need in here, there are a few different types. A big one is filtering, right? So you have to be able to distinguish all these different frequencies. And that requires, essentially frequency selective filters. There's an even sort of more important job, which is really hard to achieve, which is what's called a duplexer. And that's basically to prevent the following. So when I send out a radio frequency wave from my cell phone, it's broadcasting with about a watt of power. That's so that it has enough power to reach the next base station with enough power that it's well above the signal noise there, right? When I receive a signal on the antenna that's coming in, that might be as small as a picowatt. Okay, so there's this enormous difference in power that your phone can receive and work with and broadcast. Okay, so you can imagine that if you had any of this 1 watt transmitter leak into the very sensitive electronics for this receiver chain, it's going to completely overwhelm it, right? It's going to swamp it. There's not enough dynamic range to handle that, and you'll basically not be able to receive anything, having a small amount of leakage. So the way that you handle that is you just have a little bit of frequency separation, okay, between your transmit channel and your receive channel. And then you have a filter that basically has 2 non-overlapping passbands. So you send information at a different frequency that you receive it. And because you don't want to waste a bunch of this sort of precious spectral content, right? There's only so much spectrum in the world. Well, you think it's sort of like universal, but it's really just the FCC. But it's like very tightly regulated where you can use spectrum. And so you're trying to pack as many users in, as much information as you can. And so you don't want to waste sort of spectral bandwidth. So you want to get these non-overlapping passbands very close together. And that requires very, very low loss filters, right? If it's very low loss, then it will decay slowly in time. Then it'll have a narrow spectral, frequency passband. And so then I can put them closer together and have, a smaller amount of coupling between the 2 passbands that are neighboring, right? So the name of the game is loss. If I make, if I take microwave transmission lines or lumped components like resistors and inductors and capacitors at these, gigahertz frequencies, I'll get quality factors for resonators, filters that are in the kind of like 50 range. But phononic devices, in materials like lithium niobate and aluminum nitride can achieve, quality factors that are in the thousands at the same frequency. So basically, phonons are less lossy than microwaves at those frequencies. Now you could, let me fast forward to the other components that you need. So that this is like a filter. There are many other filters I'll explain in a second. But let's just take this like receive chain, right? So I'm going to go through this duplexing filter. The receive, this very small amount of power is going to come in here. Now I'm going to amplify it. That's the first thing that will happen. Okay. And this amplifier needs to be, very good. Obviously, it needs to have very low noise figure and a high gain. But it's going to create a bunch of frequency components that I don't want. All amplifiers do. And since this signal is very small, if I'm creating these other frequencies, they could potentially interfere and cause noise, when I essentially get to the digitization stage down here. So I have a filter here to reject those unwanted frequencies. So there's another filter here that's also very important. Then we have a mixer, okay, and the mixer's job is actually to convert the frequency down. So I'm going to take it and I'm going to make one sort of, moderately sized step between, let's say, 2.4 gigahertz here and maybe like another gigahertz down or something. And the reason is basically because I don't want to do further signal processing in ways that might cause like multiple reflections that will interfere with each other. And so changing the frequency in a sort of large step here can prevent like self-interference in the circuit and make it more robust. So I have this mixer that will down convert the frequency a little bit. And then I have another filter because this mixer also produces unwanted frequencies. And then I have another amplifier and more mixers and filters. And eventually I'm going to set this thing all the way down to basically the raw data rate. And then that's going to get digitized by this A to D converter and put into your computer on your phone, right? That's how you essentially get information from radio waves. And it's very, very similar in the opposite direction. I'll take my digital data, I'll use that to drive IQ modulators, essentially like phase coherent modulators. I'll do some filtering, I'll mix them up to a higher frequency. And then I'll filter that out. I'll mix it up to an even higher frequency and filter that out. And then I have a big power amplifier and driver to get that up to a watt and then send that out through this duplexing filter out to the antenna. So that's kind of the whole thing. Okay, so now you know how radio frequency front ends work. Okay, now let's talk about what they're made out of. Okay, so all of the filters, they're all made of piezoelectric materials. Why piezoelectric? Well, really because you need crystalline, low loss phononic materials. And that's sort of, step one. Step two, or I guess like criteria two, is that you also need to be able to transduce from radio waves to acoustic waves, right? If you want to use those low loss phononic resonators as filters, you better have something that can transduce between radio waves and phonon. And so that is naturally piezoelectricity, right? Piezoelectricity is the intrinsic coupling in a crystal between electric fields and strength. So it does exactly what you want. Okay, and so all of the things in red boxes, those are piezoelectric. All the things that are not in red boxes, those are made of transistors. Okay, so all of your amplifiers and your mixers and switches and phase shifters and oscillators, they're all made from transistor-based technologies, primarily CMOS and gallium arsenide. Okay, and they've been trying for 50 years to replace these filters with things made from transistors, and it's basically impossible. Even if you could match the performance, they burn a lot of power. And of course, people don't like RF systems that burn lots of power to achieve functions that can be done completely passively and even better. So we're kind of stuck in this paradigm inside your phone where I've got a bunch of different chips, some that are piezoelectric acoustic wave chips, and some that are transistor chips. And they're assembled together in these things that are called multi-chip modules, which is just a really sophisticated kind of interposer chip that's very carefully designed to minimize crosstalk and capacitive coupling and make sure that the bandwidth of transmission is very high. So these are kind of complicated little beasts, but in the end, they're basically just sort of flip chipping these other, all these little filter chips and the transistor chips onto this backplane that does the electrical connectivity between them all. Okay, so this does a couple of things. So first of all, because this thing's pretty big compared to the size of the chips that are sitting on it, right? And a lot of that is that you need to be able to actually handle these chips. So each one of the chips is sort of bigger than it needs to be just for the core functionality of, say, the transistors or the acoustic filters. Okay, and that's just for sort of mundane reasons, like I need to be able to pick it up in some kind of tool and make millions of these things, right? Flip them onto this interposer chip and bond them. I also have to have extra area where I'm going to interconnect this backplane to the individual chips, right? There has to be somewhere on that chip, there has to be a via that goes between the two levels, right? The two chips. So I have to have all this area dedicated to just basically electrical connections, okay? Chip-to-chip electrical connections. And then this chip itself is has to be very carefully designed to make sure that you don't have a bunch of microwave crosstalk essentially. So the size of this chip is actually much bigger than it needs to be. And this is sort of fundamentally why you don't have as good of a as you have an iPhone. Okay? You can basically fit most of the processing power that you need in an iWatch, but you can't fit enough radio frequency signal processing into an iWatch in the form factor lab. Okay, so I won't go through the argument or anything like that, but I'll sort of fast forward and say that if you could do this all with acoustic waves, and I'll tell you how, you could basically shrink this RF front-end module, which again, there are many in your phone, right? For every single frequency band. You can shrink each one of them by about a factor of 100 for a given amount of bandwidth. Okay, so much smaller radio frequency signal processing for a space in your phone. Okay, and then the second thing is that every time you do this transduction from electrical waves, radio waves to acoustic waves and back, there's loss, right? And all that loss adds up. I mean, if you follow it through here, right? It's this is electrical, this is acoustic, this is electrical, acoustic, electrical, acoustic, electrical. It's back and forth through the whole chain. It happens many, many times. There's actually sort of a lot of loss that eats into your signal to noise, right? And of course, you can make up for that a little bit by amplification. But amplification has noise. So again, you're eroding your sort of your signal noise budget for your whole system and changing sort of the minimum detectable signal that you could have. So if you didn't have to do all this transduction, then you have both a smaller radio frequency signal processor and you have a higher performing radio frequency signal processor. Okay, so but I already said you can't make these filters in transistor-based technology. That's been tried a lot. So what my group has been doing is trying to flip that on its head and asking, can we just actually replace these transistor-based functions in the acoustic domain? Okay, and so that's what I'm going to talk about for a while now. Okay, so to understand how we replace those transistor-based functions, first we should say that these acoustic waves in solid-state materials, they are completely linear, reciprocal, right? So they don't have the ability to do the functions that are necessary. We need to sort of somehow endow them with new properties. And this is how we're going to do it. So if I have an acoustic wave in, say, a material like glass, a surface acoustic wave in particular. So surface acoustic wave, just imagine this, this is glass or something, and I give it a little flick. Some of the energy in the acoustic waves is going to actually stick on the surface. And you can have these fully confined modes that will be guided by the boundary conditions alone that will live on the surface and propagate along. And there are different kinds. This is a Rayleigh wave. You can have things called love waves, and I'll say more about different types of waves as we go. But there are these surface confined waves. Okay? And the reason we want surface confined waves is because I want to launch these things with electrodes, right? I need to couple to them. I need to produce them and I need to detect them. And if they're buried in the bulk of the material, then I can't really detect them very easily. So I want waves that are confined to the surface so that I can put electrodes on the surface and very strongly couple to those acoustic waves, right? You can imagine if all the energy is down in here and I can only couple to the surface, it's pretty hard to couple. Okay, so that's why I want surface acoustic waves. Now in a piezoelectric material, in addition to this acoustic wave here, and again, this is like a simulation propagating left to right, this is the associated electromagnetic wave. Okay, now these electromagnetic waves, they're quasi-static. It's really just basically that, this thing is straining this piezoelectric material, in this case lithium niobate, and that's going to produce an electric field that's propagating with the acoustic wave at the same speed, with the same wavelength. But of course, it's not confined to the material because it's an electromagnetic wave. So it lives outside, it has an evanescent tail that's equal to the acoustic wavelength, essentially. And so that gives me the ability to interact with stuff that's on the surface. Now, what kind of stuff do we want to interact with? Well, let's do this little thought experiment. Okay, if I had a bunch of charge that I could, let's say I somehow use lasers or something to confine them to the surface so that they can completely freely move around on the plane of the material, but they can't move out vertically. Okay? Then if I have a surface acoustic wave that were to propagate through my material, then that electric potential that it's generating is going to do a couple of things. First of all, it's going to try to bunch and anti-bunch that charge. Now this is very pathological, right? This would be for a very large electric field, so it's almost bunching into line charges. Okay, but just imagine this is sort of much more gradual than that. There's a little bit of compression and a little bit of rarefaction of the electrons. Okay, so it's going to bunch and anti-bunch them, and then it's also going to try to drag them along because those acoustic waves are moving, and so those potentials that are interacting with the electrons are moving across the surface, and they want to try to drag the electrons along with it. It's a phenomenon called Coulomb drag, but it's not very complicated. It's just if you imagine you had an electron and a potential that was sort of weakly trapped, and you drag the trap, it's going to want to drag the electron with. It's just that simple. Okay. Now, I don't have to make that passive. I can actually flow these electrons by applying electric fields. Okay, and it's a lot of math that I don't need to go into here, but it's exactly the same physics as a free electron laser or what's called a traveling wave tube amplifier. But this phenomenon of Coulomb drag and charge bunching produces an exchange of kinetic energy between these two essentially waves, right? So I have one that's this electronic wave, essentially, this driven electronic wave, and I have this acoustic wave, and they can exchange kinetic energy. And it turns out that the exchange of kinetic energy, the sign of it is just dependent on the relative velocity. If the electrons are moving faster than the acoustic wave, then they give the acoustic wave their velocity, their kinetic energy. Okay? If the acoustic wave is traveling faster than the electrons, it will give the electrons its kinetic energy. So I'll get amplification or attenuation depending on which one is moving faster. And of course, if they're moving in the opposite direction, then basically the electrons will heavily attenuate the acoustic waves. But this allows me to create an amplifier, right? If I can just get those electrons moving faster, they'll donate their kinetic energy in a phase coherent way to the acoustic wave, and it will amplify as it travels. Okay, so now it's probably worthwhile talking about some of the physics here. Okay, so in order to get this kinetic energy exchange to happen very strongly, you sort of consider the time scale over which it happens, right? So if I imagine this acoustic wave is moving more slowly, this electron, these electrons are sort of moving past it. They're interacting, but only for sort of a finite amount of time. Okay, and while it's sort of interacting with the closest acoustic wave potential, the electrons are sort of responding, most strongly to this local sort of crest and trough. If that crest and trough stay around forever, then the electrons are going to move into a position where they basically clean out the field, right? It's as if you have an infinite conductor in that case, right? Because what an infinite conductor really is a conductor in which the electrons can move infinitely fast. And what do? They move and they screen out fields. There's no electric field inside a perfect conductor, right? That's like sort of intro EM physics, right? So if I give them enough time, if they can move fast enough compared to the rate that the acoustic waves are moving, then there won't be an interaction at all. Okay. So on the other hand, if they never move, if they literally don't move at all, so that they can't screen anything, essentially they're just stationary because the electrons have such a low conductivity that they never move for any of the crests and troughs, then I'll also get no interaction. So there's kind of two regimes, right? I get nothing, okay, if there's very low conductivity. I also get nothing if there's very high conductivity. And there's actually sort of an optimal conductivity where the time constant for the electrons to respond to these electric potentials is equal to the period of the acoustic waves. Then basically every acoustic wave sort of maximally move each electron bunch, and then the next one will come by and it'll move it back. And I'm basically extracting the most kinetic energy I can from these little electron bunches as it goes. And so this time scale is actually engineerable, right? We're gonna talk a lot about time scales as we go. But what I want to do is I want to control essentially the rate at which electrons move around this material system to be close to the period of the acoustic wave to get maximum energy transfer. Okay, so disappointing news. It's basically impossible to trap electrons on the surface like that. I mean, I guess there are electron and helium experiments. So rather than trapping electrons, we're gonna sort of trap them inside of materials. Okay, and so what we want to do here is we want to put some kind of semiconductor on top of our piezoelectric material. Okay, and when we do that, we have to be mindful of these various constraints. So the first constraint is that I need to get the electrons moving faster than the acoustic wave. And that generally means I need a high mobility semiconductor, right? Mobility is this property of semiconductor materials. It essentially governs how fast they move per unit electric field you apply. I don't want to have to apply enormous electric fields, both because applying electric fields, that large would be very challenging. Maybe make the system like, susceptible to arcing, to other stuff in my phone. But also, the larger the field I apply, the more current's going to flow, and that's Joule heating, right? That's just dissipation. So for both reasons of power efficiency and just not having big electric fields around, I don't want large electric fields. So I want high mobility semiconductors. That kind of limits which materials I can pick. I also need it to be, it turns out in the gigahertz frequency range, if you sort of look at the available range of carrier concentrations you can get these semiconductors in, and the thickness is available. The only way to make this time constant sort of optimal for the acoustic wave frequencies you need to use is to make them very, very thin and very, very high resistivity. So I'll have a very low carrier concentration and a very, very thin semiconductor material. And that's the only way it'll work. If you make these very thick or the conductivity is very high, you just won't get any gain, okay, in these amplifier devices. And so we have to figure out a way of getting this very, very thin material on top of this lithium niobate. And what we do is the following. So we grow this other wafer here. So we have one wafer here. This is like either all lithium niobate, or in our more sophisticated devices, something like silicon with lithium niobate thin film. And then here we have this indium phosphide wafer. And we grow this series of epitaxial layers that are all lattice matched. So they can be nice and thick, and there's no defects. Okay, it's use the technology called MOCVD, if you're familiar with that. Metal organic chemical vapor deposition. There's a couple of Nobel Prizes that won for it. So it's you should look it up if you don't know about it. It's very cool. It's a way to basically grow very thick, high purity epitaxial semiconductor things. But the important point is I can grow these stacks of alternating indium phosphide and indium gallium arsenide. Now, why indium gallium arsenide? Why indium phosphide? So indium gallium arsenide is important because it's one of the highest mobility kind of easily available materials that you can make. It has a bulk mobility of 10,000 centimeters squared per volt second. That number may not be very meaningful to you, but silicon is more like 1,000, 1,400 actually. Okay, so it's a very, very high ratio of the velocity per electric field for a kind of just easily growable semiconductor material. This red material. Okay, indium phosphide is just there because that's a good substrate for it. Okay, you can actually just grow MOCVD on indium phosphide. It's also important that these I can grow with good chemical orthogonality. So I can use different acid chemistries to only etch indium phosphide and not indium gallium arsenide and vice versa. And that is going to allow me to do the following. So I'm going to bond this wafer, now flip it upside down and bond this surface to here. And I'll have a very, very thin cap here. This is just basically like protecting this top surface. So it's not really doing much. The action is all right here in this second layer, okay? So I need to get all this stuff going, okay? By the way, this is a scanning confocal acoustic microscope image. It basically use acoustic waves to image through the bonded material to see if there are any voids. So we can kind of, before we do a whole bunch of extra processing, we can see like how much of the area actually bonded. You can see there's a couple little voids here, there, and there, but it's pretty much a completely continuous bond across those kind of 4-inch surfaces. Okay, so then we're going to use these orthogonal chemistries to start removing the substrate. Then we have an etch stop. Then we remove that etch stop, and we stop on the next stop. Then we start doing something a little more sophisticated. There's a couple of layers here that have a graded carrier concentration, and their whole job is to basically, get what's eventually going to be metal contacts up here to flow electrons in and out, down sort of in steps to the very high resistivity of this amplifier layer. If you just make one jump, you won't get like what's called an ohmic contact. It will have a very large offset voltage. It'll be hard to work with. So if you want to make an ohmic contact, there's sort of special metallurgy, or it's not really metal. It's sort of a combination of metallurgy and semiconductor materials physics that you can use to sort of engineer the band structure of these compound materials to make a nice ohmic contact to this very, very high resistivity layer down here. And then, so after we sort of pattern those contact layers and pattern the amplifier and deposit a couple of different metal levels, one is like this special metal that's there to sort of make this precise metallurgy contact between the semiconductor films and whatever metal I need to use. And the other one is just aluminum for launching and receiving acoustic waves. So the devices actually look like this. Okay, so here's a wafer of all these devices. Here's kind of a very zoomed out SEM image. So this is an interdigital transducer. You can see sort of a zoomed in one here. So it's a bunch of interleaved metal fingers that are going to be at the same period as the wavelength of the acoustic wave. Okay, and that will basically create an acoustic resonance for the specific frequency I want to launch. So I pick what frequency I want based on how I design these interdigital electrodes. Okay, and now you can see here these other materials. So this is the amplifier layer. It's about 50 nanometers thick. We get about 70% of the mobility of the volt materials. We get 7,000 centimeters squared per volt second. 50 nanometer film that's not even protected on the top. If you don't do semiconductor material, it's not very impressive, but it's kind of surprising that it worked that well. And then we have this contact that I sort of drew as that little like sort of mesa structure. That's this, and there's the big thick metal contacts that make contact to that. Okay, and then there's an aluminum IDT. So that's kind of the whole thing. And if we launch acoustic waves in this direction, okay, and then we apply bias fields from here to here, then we can measure essentially the transmission of this device's function voltage and characterize its operation as an amplifier. So how well does it work? Well, it took us a while to get here. But as of say last year, this was how well they were working. So in about a 500 micron distance with a phonon frequency of 1 gigahertz, we can get about 28 dB of acoustic gain. So that's the acoustic power, entering the device on the left, which we can calibrate, is about 1,000 times smaller than the acoustic power we get out. 28 dB, so pretty close to 30 dB. Okay, and the noise figure for the phonons is 2.8 dB. So that means that I've degraded the signal to noise compared to the input spectrum by about a factor of 2. Now, this is actually pretty close to as good as a microwave amplifier would work for microwave. So if you just go to like Pasternak or something and you look up low noise amplifier, this is not that far off for like a high performance microwave amplifier. And that's a technology that is, say at least 50 years old. Okay, so and as I'll talk about in a second, we're like pretty far from optimal performance here actually. Now I mentioned that if you turn the acoustic wave around in the opposite direction, it will be heavily attenuated. How much? Well, we get about 44 dB of non-reciprocal transmission, meaning that it's a little bit more than 20,000 times higher transmission in the forward direction as attenuation in the backward direction. So very, very non-reciprocal. The bandwidth of the amplifier, so again, the center frequency is designed to be about 1 gigahertz, but we can sort of put multiple of these IDTs down in the same wafer and characterize the bandwidth of this sort of single layer of material. And we have about a 3 gigahertz bandwidth. So it's very, very broad band. right? It would be like we had a laser amplifier that went from 50 nanometers like up to twice that frequency, right? And down to about half that frequency. So it goes from about half a gigahertz to 3.5 gigahertz. So incredibly large bandwidth. And this one burned about 20 milliwatts of DC power. Okay, now let me tell you about why that's significant. So 20 milliwatts of DC power, that's all being dissipated basically in the semiconductor. And it doesn't really, the only place it has to go is down into the silicon substrate. It has to go through the lithium niobate, but that's pretty thin, just a few microns. And then it goes down to the silicon, it has to get away, right? If it doesn't get away, then it's heating up. And if it heats up, then the carrier concentration will go up. And then you can actually get this runaway thermal process where you put in a little bit more power, it heats up the device, that injects more carriers, that makes the conductivity higher, more current flows, more heat gets produced, and it just runs away. So you'll get, basically the device will melt. So we're kind of looking for ways to improve on that. And we just published this paper doing that. So this system is very, very similar. We still have the indium gallium arsenide semiconductor, but we've replaced the acoustic material, the piezoelectric acoustic material with aluminum scandium nitride, which is another piezoelectric material. It's not quite as good as lithium niobate, but it can be really nicely just sort of sputter deposited on top of silicon carbide. So aluminum nitride with no scandium in it is perfectly lattice matched to silicon carbide. And aluminum scandium nitride is a little bit mismatched, but you can just sort of slowly increase the scandium concentration as you grow it. And you'll get like relaxation that will not cause dislocation. So you get this really nice film that's perfectly lattice matched at the interface, and you can grow very, very thick. This is about a 1 micron film. Then we bond the semiconductor on the top, same as we've been doing. Now, the big thing here is that the silicon carbide is like almost as thermally conductive as a metal, right? It's 3 times more thermally conductive than lithium niobate, then 3 times more thermally conductive than silicon, okay? So we get essentially a third the temperature rise per unit power. So this one, we're actually able to basically completely saturate the gain. The physical mechanism for saturating the gain is actually kind of cool. The electrons are just going as fast as they can go in the semiconductor. This concept of mobility is like the linear regime for applying electric fields to carriers. At some point, they just essentially reach terminal velocity inside the semiconductor. It's essentially determined by how often they scatter, right? So but the carriers are reaching terminal velocity here. So, and that's actually not even like sort of the theoretical maximum of the gain, but it's at least like the maximum this device can produce. Now this one is producing about 40 dB of gain, so about a 10,000x increase in power. This is operating at 3 gigahertz, a little higher frequency. What's more significant than those things is that growing semiconductor materials is hard, and we are always trying to drive the carrier concentration lower, and every once in a while we get lucky. This device happened to have pretty much ideal carrier concentration, and so now the power consumption was about 2 milliwatts instead of 20, just because of the semiconductor properties. Some sort of unfortunate that it's hit or miss, but that's just sort of the name of the game, and this was good growth. So good growth led to good power consumption. So now we have basically, it says 6, but it's actually 2. 2 milliwatts of power consumption, 40 dB of phonon gain. So kind of marching up in performance there. You can use these things for more than just amplification, right? You can make a switch. So if I have, you can think of this thing here as an acoustic beam splitter. It's called a multi-strip coupler. So if I shoot phonons into one side, it will basically produce an equal amplitude of phonons going in the same direction over here. And then I can determine, I have a couple of pairs of, I have a pair of amplifiers here and a pair of amplifiers here. And if I just basically, forward bias them here, I'll get gain or say like unity transmission in this direction. And I can bring it to the, so that they're oppositely polarized here, and I'm getting heavy attenuation. So it'll go through this channel, or if I flip those voltages, it'll go through this channel. So that's how you can make an RF switch. That's an important RF component in those signal processors. This is what's called a circulator. So this is, remember I said that the way that we separate the frequencies on these chips is by the way that we separate transmitted and received signals is by frequency. Okay, there's another way to distinguish them, which is by direction, and that requires breaking reciprocity in your system. Now, the normal way you break reciprocity in RF systems is use what's called a gyromagnetic circulator, which uses essentially a material that has the RF equivalent to the magneto-optic effect, right? So you all have probably Faraday isolators in your labs for your lasers. Every laser that you use probably has a Faraday isolator in it, which uses the magneto-optic effect. The gyromagnetic effect is the RF equivalent of that, and produces non-reciprocal transmission, non-reciprocal phase accumulation essentially for RF waves, but they're big. Okay, if you actually look at one of them, they have to be wavelength devices because you're actually using wave interference to create the non-reciprocal transmission there. And so they're like, sort of at 2.4 gigahertz, it's probably like the size of like a pretty big point cell battery. It's bigger than every other RF component in the system combined. So you don't use circulators in cell phones. Use them in radar systems where you're not space constrained. Okay, for sure. And there you're just separating signals because transmission's going one way and receiving, the received signals are coming the other direction. But now we can make these circulators on chip because we have very, very high non-reciprocity. And so we can just actually, you can see how to use it. So we have 3 ports. Each of these individual transducers will launch a wave to the left and to the right. If we just bias these amplifiers here, I should say that this device here is a sort of another. It's like a very cool acoustic beam splitter. It will produce, for an input wave here, it will produce 100% reflection in a different spatial track down here. So the input waves come in this sort of track. They're just, this is. You should also keep in mind that we're just talking about collimated acoustic beams here. So if you just sort of, in the same way that this laser is collimated, right, because it's the diameter of the beam is such that it has a very, very long Rayleigh range. We're doing the same thing here. Our individual transducers produce a wide acoustic plane wave that's it gives it a Rayleigh range that is much larger than the device. So these things are just collimated acoustic beams. And so if I have this collimated acoustic beam come in on this track here, it will basically be reflected at 100% roughly in this track down here. And so it's a way to make sort of a ring device. And now if I take these 3 amplifiers and I basically bias them so that this one's forward, this one's forward, this one's forward, this direction, that way. Okay, then one helicity has basically, transmission and the other one has heavy attenuation. So I can make a circulator basically that will only allow waves to travel around in one direction in this ring, and then I have 3 ports to basically read out each one of these portions of this wave. So you can make circulators this way. Okay, so now we're going to talk about mixing. So remember in that first sort of blender image I showed, I showed those electrons as being really, really polarized, almost like line charts. Okay, that's like very pathological. Okay, but if you did that, then what you've essentially done is you've taken the susceptibility of this media, right? The electrons and their distribution govern how the acoustic waves can propagate underneath, right? And so if I pump this thing with a really, really big acoustic wave amplitude, I'll actually produce a susceptibility that is both spatially and temporally varied, right? The electrons are moving and they're like moving as line charts. So I have this very, very strong spatial and temporal perturbation moving through the system, okay? So that's exactly the same as occurs in nonlinear optics, right? If I pump a nonlinear optical crystal with a very, very large amplitude optical wave, I'll produce this moving polarization wave in the material that has a spatial and temporal modulation, okay? And then if I put in other waves, and I look at the sort of the Taylor series of the susceptibility of the system, I'll see that it results in products of fields. And it's exactly the same here. So I get product interactions between multiple fields, and if I put a really strong pump in, I can basically turn the system into a sort of a parametric device where I can do things like, this is showing three-wave mixing, where you can get things out at, say, the sum frequency. So I can put in this pump at omega 1, put in a signal at omega 2, and get out an idler at omega 3. And you can have other kinds of, you can do difference frequency generation. You can do parametric amplification. You can do all the three-way mixing interactions you can in nonlinear optics, but in this case in acoustics. As I'll show you, the nonlinear interactions are very strong. They're created by this semiconductor amplifier, semiconductor material. We can just like fully derive the susceptibility in this case too. It's kind of interesting. Like, it's much more difficult to derive the nonlinear optical susceptibility because it involves like the wave functions of the actual atoms in the lattice, right? But here it's really just sort of these bulk semiconductor properties. It's kind of the drift diffusion equations for the electrons, the piezoelectric acoustic equations for the acoustic waves, and you can just fully derive this nonlinear susceptibility. All the nonlinearity kind of comes from this nonlinear source term here, which has like the product of E and the divergence of D, right? So it's like not easy to solve, but you can at least write it down in closed form. So let's talk about the actual. So before I get onto the device, let's talk, I guess, just for a second about three-wave mixing. it's interesting, you know, just like I said, you can write down this susceptibility. So, or you can sort of solve for the nonlinear coupled wave equations, I should say, and then you can derive the nonlinear susceptibility and expand it in, you know, powers and fields. And for three-wave mixing, you can you know, you just fully derive three-wave mixing susceptibility. And it has like a really similar form to the nonlinear optical susceptibility. We'll find some things where, you know, we get, it's obviously proportional to the strength of the electron-phonon interaction, which is usually quantified by this quantity called k squared. It's proportional to the mobility, which is interesting. So the more mobile the carriers, the faster they can respond to the electrons, to the acoustic waves fields, the more nonlinear it'll be. And then we have these sort of resonance factors, and these resonance factors are the same resonance factors that govern the exchange of kinetic energy in the amplifier system. So basically, I need to sort of now think about trying to do some kind of collective matching of the three acoustic wave periods I'm going to use and the electron response time, which I can't make it the best for all three wave frequencies, right? But I can find, you know, what frequency, what electron concentration is going to give me the best sort of time constant to maximize these sort of susceptibility factors for all three wave frequencies I want to use. So it's a very highly engineerable system. It's also a little bit complicated, right? But nevertheless, we make them and we see how they work. So this is a sum frequency generation device. It works as follows. There's a IDT here. So this is to generate, you know, omega 1. And then it's going to go through the transducer for the signal. This is IDT2. And you can see that that this is like very, very fine pitch, and this is a much less fine pitch, so I can actually resolve the fingers here. Okay. The reason that I'm going to shoot this one through that one is because I'm going to call this my pump, and I just want my pump to be really big, but I'm actually interested in the conversion efficiency of the signal frequency, right? Just like if I were doing like some frequency conversion in a Tipton crystal, I really care about how much of that, you know, input signal frequency I get out of the item, right? And so I don't want to shoot the signal through this IDT here that might like reflect a bunch of the wave away. Okay, but with the pump, I can just put in more power. Okay, so I'm going to put this really strong pump through. It's going to travel until it gets underneath the semiconductor, and then I'm also shooting through this omega 1 field. And then I have this output IDT, okay? And I can basically choose whether I want to look at some or different frequency conversion here. So I can put, I can choose the pitch so that the sum of the k vectors here and here matches here, and if the frequency also matches for that, then I'll have a phase match interaction. And so the three frequencies I pick are here. So this is the signal, this is the pump, and this is the idler. You know, you can see that the signal frequency is almost, you know, it's like 2.5 times larger after this sum frequency interaction. So this is just sort of characterization of them. There's no sum frequency generation going on right here. Okay, sum frequency generation is happening here. Okay, so this is the spectrum. If I scan the frequency on an electronic spectrum analyzer, if I look at the spectral content of the output as a function of power of this pump field here, then I can see that you know, I have basically this increasing amplitude for the idler wave as I increase the pump power. And actually, this should say 0.0006. So that's that. So we go from 0.6 from 0.0006 milliwatts to 0.6 milliwatts, and then you can see this increasing efficiency of conversion. If we just take this peak power right here at the peak of the conversion, and we plot that as a function of pump power, we're actually getting about 16% conversion efficiency for this signal to idler, all for phonons, right? So this is pretty good, right? Like if you go and you buy a commercial Tipton crystal for doing some frequency generation, 16% is not bad. And again, like we didn't actually do anything to try to specifically engineer those time constants I was talking about for these three frequencies. We also didn't try to engineer very carefully the phase matching for these three acoustic waves. The reason is because we were just trying to do something and do a proof of principle. But more to the point, it's actually just a really complicated system to engineer. We're kind of constrained in the lithium niobate thin film thickness we can pick, which completely determines the dispersion of the waves. Like I said, growing the material is very challenging, and so like in order to like sort of optimally pick that carrier concentration requires oftentimes better precision in the carrier concentration that we can actually achieve. So going forward, we'd like to be able to try to optimize this. And we think actually it should be possible to get to essentially unity conversion efficiency. But 16% is pretty good for a first pass. I will say we also did difference frequency conversion. We didn't just sort of turn the device around and operate it in the sort of reciprocal kind of system. Here we were interested in doing something that was more like that baseband down conversion, the last step of the last step of like stepping the frequency down to the baseband signal in a radio frequency signal processor. So we're going in this case from 250 megahertz down to about 100 megahertz. So the signals at 250, idlers at 100, and the pumps, at the some of those. So in this case, because we're using this very, very long wavelength acoustic wave at 100 megahertz, it has a significantly slower wave speed than the two higher frequency waves, which kind of only see the lithium niobate. This one has a much longer wavelength, so the frequency is lower, and so it's like interacting more heavily with that silicon substrate, and that ruined the phase matching basically. And so we only got about 1% conversion efficiency here, but again, with sort of optimal phase matching in this system, we could easily get this back up to be as good as the some previous generation. Okay, so last thing to say is like none of that was biased, right? Those bias fields are just off. We're not amplifying anything, but you can amplify, right? This thing can easily you can flow current in the same direction as you're doing the thing. And in that case, you're both amplifying the pump, amplifying the signal, and amplifying the idler all at the same time. So it's a really kind of complicated nonlinear mixing interaction where all three fields are kind of growing, both because they're being, sort of linearly amplified as they travel by the amplifier function, and because there's this spatial dependence of the growth of the idler wave and the attenuation of the signal wave as they propagate through. And the pump is growing, right? Usually you think about sort of a pump as having a constant amplitude over the length of the interaction, but in this case, the pump is growing. But the net effect is that you sort of, if you didn't know that you were applying those bias fields, and you ask about, well, what's the conversion efficiency? It just looks like it's artificially getting better, right? You just sort of see an artificially enhanced conversion efficiency. Now there'll be noise added because it's amplifying, but it's sort of interesting that you can increase the effective conversion efficiency. Okay, I'm gonna just fly through this because we're getting short on time. I don't want to talk about quantum stuff. This is Q farm, not just farm. But I will say that one of the really important ways. So if you think about the fact that we're all using the same airways, right? Like in other words, we all have the same airspace here. We all have our cell phone signals are all coming in, and somehow we're receiving them. You're not receiving mine, and I'm not receiving yours. Okay, that's because of encoding. Okay, there's different kinds of encoding. But it's really important function. It basically is what allows us to all share the same frequency spectrum, but not look at each other's signals. And so they're all encoded digitally by modulation. And then you have to do a function called correlation, essentially cross correlation, to reconstruct the signals. So there's this complicated process of what's called spreading and despreading that happens by applying a code. And the easiest way to think about it is sort of, one way to do it is frequency hopping. So you can just think of it like, instead of just having one carrier frequency at 2.4 gigahertz, I'm gonna hop around a bunch, okay, and just randomly place where I'm actually transmitting at any one time. And so I'm gonna take my very narrow band frequency here with a large amplitude, and I'm gonna spread it across a very large bandwidth by hopping around periodically in time, okay? And that's gonna lower the actual signal I'm sending to you, and you, and you, and you, and even me, right? Like below the signal to noise, below the noise level for your system. So you cannot detect that signal unless you do this correlation function, which will unspread it and basically sort of recompress the thing back into this narrowband signal where it will be above the noise. But only you are using your particular code, okay? And so that's how you reconstruct your signal to get it back above the noise level. That's how we can all kind of share the same radio waves. So this function of correlation is actually critical. Now, what I will just say really quickly without kind of showing you how is that if you launch two acoustic pulses at each other, and you put them underneath this electrode here is a semiconductor, you can show that basically when they're overlapping underneath this metal electrode in the semiconductor, the integral of the current, which I get because I basically just have one electrode here, the integral of the current will give me the correlation at twice the frequency of those two pulses. So if I launch basically two identical pulses at each other that have the same code, I'll get a reconstructed signal that's the correlation of the two at twice the frequency. So I still have to I have to deal with the fact that it's doubled in frequency, but I've done the correlation. And we're actually using this to make correlators. And we've now demonstrated the correlator. This is So our best lab results right now are about 400, what's called tera operations per second per watt. Now, tera operations per second is trillions of operations per second per watt. Operations, okay, we're not doing any operations, this is all analog, but what we're comparing to is a correlator that actually is doing mathematical operations in the digital domain. And the most efficient way you can do that right now is about 5 tera operations per second. It's essentially, Fourier transform, right? So it's doing a bunch of multiplication and addition, right, to do the Fourier transforms. But the best efficiency that can be done right now is 5 tera operations per second per watt. Because we have such large nonlinearities in these systems, we're getting about 400 currently, and we project that we can get out to about 2,000 probably in the next few months just by improving the device performance. So right now we're currently getting about a factor of 80 better efficiency than the state of the art, and we think we can get into kind of like 400 or more better efficiency. So this is a pretty cool application of this technology. It's also like a much more sophisticated device. We have to pre-amplify our signal, right? You receive these small signals. In order to get the nonlinear reaction to be large enough, we have to amplify this incoming signal, okay? So that this one is just, you think of this as sort of like, this is on your chip, and this is launching this reference waveform that also has your code. But you've received this small signal over here, and now you want to mix them together underneath this electrode. So we pre-amplify the weak signal, feed it against the strong signal that comes from the system, and this is how we sort of increase our nonlinear efficiency. But of course, the amplifier is burning power, and so that sets our power dissipation for the system and determines our efficiency. So anyway, that's how we're going to sort of get to this 2,000 number, is by making better epitaxial material that dissipates less power. But it's pretty cool. So I'll just say really quickly that we can make parametric amplifiers. So this is a degenerate parametric amplifier. It is producing phase-dependent gain. This is at room temperature. So we measure things like thermal noise squeezing, but we are currently, well, I'll tell you more about all the quantum stuff right now, but we're currently doing this in a way, we're sort of just putting together our dilution refrigerator right now to do these things at cryogenic temperatures, where we can actually do this in the quantum domain. And I'll say more about that in a second, but I'm going to go a little bit faster here. Let me just say that we can also measure degenerate four-wave mixing, okay, which is essentially the current nonlinearity. Now, Professor Safaviani has this great paper where they measured four-wave mixing for acoustic waves in a waveguide in lithium niobate on sapphire. Okay, so they launched acoustic waves in this lithium niobate waveguide, and basically what they did is they put 2 pump tones in. So they have a pump at omega 1 and a pump at omega 2, and they generate this curve cone. Okay, because I can absorb 2 of these phonons and emit one of these and get a sideband over here, or I absorb 2 of these phonons and emit one over here to get this sideband. And then those can remix and form this what's essentially a curve cone. Okay, and that curve cone, the ratio of those sidebands to the pump power you use tells you what the current nonlinearity is. And in Professor Safaviani's paper, they have this very narrow waveguide which increases the effective nonlinearity. They got about 15 per milliwatt squared for their effective nonlinearity for this four-wave mixing process. So if we just take our focused acoustic waves, it's not quite as good, but we shoot them through this acoustic. We just shoot them through lithium niobate, and so they're just not as focused. So it's basically the same as this demonstration, but they're not quite as tightly confined. Then we get something like 3 per milliwatt squared, right? So that's just saying that if you confine them a little bit more, you get higher nonlinearity. But basically, this is all the nonlinearity from lithium niobate alone, right? Just that lithium niobate is a little bit acoustically nonlinear, right? But when we put down this semiconductor for our system, we get a curve coefficient of about 935. So we've increased this thing by like 310x, right? So the curve coefficient has gone up by 310 by placing this semiconductor material on top. And again, we can derive the stability, and we find that it's proportional to the mobility. And so the question is like, well, how far can we take this, right? Can we make giant curve nonlinearities? And the answer is yes. So because we can make giant mobilities, if we instead of using these bulk semiconductors, we use a 2D electron gas. So we grow this instead of this this stack basically producing a single material where the electrons are confined. Now we produce this very thin quantum well heterostructure where the electrons will be confined in a 2D electron gas, which has a mobility that's close to 1,000,000. So the mobility will go up by like a factor of more than 100. It's about 250. And we bond back to the material instead, and we redo this curve cone experiment. And here we find, again, so we had 3 for lithium niobate alone. We put our room temperature semiconductor down, we get a factor of 300 increase. We're almost at about a factor of 1,000,000 larger compared to lithium niobate alone. for this 2D electron gas. So in fact, it makes the experiment difficult to do because almost any amount of RF power that you put in will produce this current home. Now, why do we want to do that? Well, here's an interesting reason why. So instead of thinking about these propagating fields producing current nonlinearity and making this home, let's think about what would happen inside of a cavity. Inside of a cavity, I'll put in a phonon. Okay, now the curve shift will basically represent the frequency of the cavity, right? Curve shift is the velocity, it's the intensity-dependent velocity of this medium now. So if the velocity inside this cavity depends on the phonon number, then I essentially have a phonon number dependent frequency for my cavity. So if I put in one phonon, it's a different frequency than two. This is how you make a two-level system. This is how transmons work, right? So transmons have a Josephson junction, which creates a nonlinearity, and essentially breaks the anharmonic, breaks the harmonic ladder of an otherwise linear resonator. Okay, so without going into the math here, we can use these propagating experiments that we've measured here, where we measure that million X increase in the nonlinearity to predict what the current nonlinearity would be inside of a cavity. And then, you know, what we're looking for is, can we produce a kerr shift that will make this harmonic ladder of states for our linear cavity without the 2-dig, and harmonic enough that we split 0 and 1 and 1 to 2 and 2 to 3 by more than the line width of the cavity mode, with the inclusion of this 2-dig, right? So the 2-dig creates the nonlinearity, makes it anharmonic, and then we could potentially think about making a two-level system here. The real answer to this question is, if we want to get to single phonon level current nonlinearity, we have to kind of really over-engineer our system. So just like I showed Professor Spagniini's work, where they effectively boosted their nonlinearity by a factor of 5 by combining to a waveguide, we're going to need to do the same thing. So we have to make waveguide versions of our system, not just use freely propagating acoustic waves now, but actually make waveguide versions of the system, so that we can increase our effective nonlinearity, just like you do in a nonlinear crystal, right? The reason that you get better efficiency for going through like a proton diffused pip-letting device rather than just lithium niobate alone, right? It's because the big reason is that you're focusing down the wave. So each photon generates a larger electric field. We want each phonon to generate a larger nonlinearity. So we need to focus these down into acoustic waveguides. We also need to make better high mobility 2D electron gases. But if we do all that, we think that we can basically get down to these single phonon nonlinearities, single phonon current nonlinearities that are larger than our cavity lines. And so we put out a theory paper, sort of describing that, and calculated nonlinear susceptibility in the quantum regime for these systems. Also calculated things like the amount of gain for a quantum related parametric amplifier. But the long and the short of this is that going forward, we should be able to make devices that look fully like the analogs of superconducting circuit quantum information processors, right? So what's inside of a superconducting circuit quantum information processor? There's a linear resonator. It's coupled to a nonlinear qubit. It gives it a nonlinear inductance that produces this single, in this case, single flux-on nonlinearity, right? They use microwaves. They need microwave flux to produce nonlinearity. So they have a single flux-on nonlinearity from their transmons, or in this case, xmons. And then they have readout circuits that are basically parametric amplifiers, right? So they have quantum limited parametric amplifiers to do the readout of their qubits, right? So that's what we want to do, right? We want to have cavities that are coupled to a nonlinearity to produce single phonon curve shifts. Okay, so same Hamiltonian as a transmon. And then we want to couple those out through parametric amplifiers to amplifier states with quantum limited additive noise, right? So the best you can do for in terms of adding noise for an amplification process for quantum systems is half a quantum worth of energy, and that only happens for degenerate parametric amplification. So again, I skipped over the slide, but we are doing room temperature parametric amplification right now in the lab, and we'll probably write this up in the next few weeks. So here we measure thermal state squeezing, which is kind of boring, but if we put this in a dilution refrigerator with this 2D electron gas, then we can hopefully measure vacuum squeezing for phonons, and produce quantum limited parametric amplifiers and squeeze states and all kinds of interesting quantum interactions in these systems. So I told you I'd get to quantum at the end, but that's basically where we're going to end it. With that, I will just skip over this whole other topic that I won't talk about, and thank the people in my groups at U of A and Sandia, and let everybody know that I'm definitely hiring for postdocs and grad students. So people are interested in working on this stuff, I'd be happy to talk. But with that, I will thank everybody for inviting me and listening.
Thank you. Questions?
I have a question about the non-reciprocity of your amplifier. And I was curious about if you could talk a bit more about how the attenuation occurs and why the attenuation doesn't match the gain.
Oh, yeah, like why it's not symmetric?
Yeah.
Yeah, it's actually pretty simple. It is that we'll go here. Okay, so actually so this is not at zero. The no energy exchange interaction occurs when the velocities are equal, right? So so it's not at zero velocity, right? There I actually already have some attenuation. I need to make the electrons travel at least as fast as the acoustic wave to get no net energy exchange. And therefore, if I turn the acoustic wave around, there's like an offset velocity I need to overcome. So that's why it's not reciprocal. That's not why it's not reciprocal. That's why it's not symmetric. But it's both non-reciprocal and non-symmetric. Yeah.
Thank you.
Yeah. Yes, sir.
You showed very nice gain and reciprocal aspect of the gain. Lots of interference in the gain, which I didn't understand.
Yeah. So yeah, like these.
Yeah.
So there's a few things going on. One is we're launching multiple acoustic modes. We only want to launch one. In fact, I didn't say it, but I meant to talk about it here. I forget where the picture is, but so the actual waves that we're using are love waves. So I'll look up it, but they're shear horizontal waves, and the reason is because they have very, very high electromechanical coupling, so they couple really strongly to the electrons. However, the Rayleigh wave is still there, and there are also other waves as well. And so we're launching all three of those at least. So that's part of why there's all this content in here that shouldn't be there. That is in principle engineerable. There's also some triple transit effects where so you can actually turn these things into oscillators. So you can have more forward gain than backward loss. So you can have it go to the end, reflect off that transducer, and get enough. There'll be attenuation in the backward direction, but then they'll get more gain in the forward direction again. And that triple transit can actually produce essentially oscillation. So if we time gate this, it removes a lot of that. So in the future, we'll probably have to think about how to get rid of that triple transit if we want to actually be able to use these where they're not so close to oscillating. Yeah, good question though.
I kind of have two questions. Sure. The first question is about the sort of the workhorse, the piezoelectric effect. In the picture, you showed that there's like two terminals, and then there's a wave that you excite.
Here?
Yeah, this one. Are those two terminals like the fingers of the IDTs, or can this just be two like terminals separated by some distance?
Yeah, these are literally just two DC terminals that are producing this current. And then what's not shown is there would be two other terminals that are acoustic only, and they're launching and detecting the acoustic current.
Okay, so could you comment on like what's the maximum sort of RF frequency you could potentially use this effect for? Like, are we talking terahertz or 100 gigahertz?
So that's a fantastic question. The effect goes away when the acoustic momentum is equal to the de Broglie momentum of the electrons. Okay, so in that case, it's you're just physically changing the acoustic momentum states of the system, and it doesn't sort of work in this parametric regime. And so that occurs around terahertz for most of these semiconductors. It's depending on materials and thicknesses and all those things, but it's kind of in the terahertz regime. No, nobody's ever demonstrated, actually, I shouldn't say that. There was a recent paper, like it came out maybe a few weeks ago, where somebody took a thin film of graphene and showed that they were getting some acoustic gain for phonons in graphene at around 1 terahertz actually. So yeah, as of a few weeks ago, nobody had ever demonstrated that. But yeah, now people have shown, not very much gain, because it's like they're much less sophisticated devices, but they definitely showed that they were getting some acoustic amplification at 1 terahertz in graphene.
And the second question is, you made this analogy between, or comparison between superconducting transmon systems and the sort of vision for the quantum vision for this platform. I kind of missed the sort of why would you?
Why would you want to do that?
Yeah.
That's because I was rushing and I didn't say it. So you didn't miss it, I did. So one big reason is the size of the qubits, right? So the typical superconducting qubit, well, let's just go fast forward real fast. You can see the size. Okay, so this is a group out of John Martinez's lab, right? So technical views at UCSD. I think this might have actually been their first Google paper, so they're publishing under both. But anyway, so you can see they're like 430 microns by about 1560 microns. Okay, so that's enormous compared to the size of what these would be, right? These are governed, this is governed by the electromagnetic wavelength at 5 gigahertz. These would be governed by the acoustic wavelength at 5 gigahertz, which is smaller by more than a factor of 10,000. So that's one reason. Now, small is not really the problem right now in superconducting circuit qubits, right? It's really like, like input and output of the RF, right? But there are other reasons. So one reason is that, the kinds of noise that these things are susceptible to has a lot to do with the fact that, their underlying physics. So for one thing, like people still regularly show that a lot of the qubits that are made are still radiating, right? You have to make these things in a box that cuts off all the electromagnetic modes, right, to get them to be high Q. We don't have to worry about radiation, right? So our things cannot radiate into free space. We can basically provide some kind of a Bragg structure underneath that will just completely cut off all the modes that we don't want. Another thing is that these are really susceptible to charge noise and two-level systems, right, that they interact with. Now, the number of two-level systems they interact with is proportional to basically how much area they take up. Now, ours take up an area that is fully like 10 to the 4 squared times smaller, right? And so the total number of two-level systems that this thing will interact with at the same frequency is a huge order of magnitude, like 8 orders of magnitude smaller. So potentially, the decoherence mechanisms might be better for a system that is intrinsically smaller. Also, there's no superconducting materials in here, right? Superconducting materials are kind of a pain. They don't like light. Have all these like vortex traps that you have to deal with, and it's just like a lot of material science to make them really good. We don't have we don't have superconducting materials. So the choice of materials is completely different and engineerable. So there's no reason to suspect that this is going to somehow just like beat superconducting circuit qubits, right? They've got a good 30 years of work ahead of us. But there's a lot of cool physics to sort of explore in terms of decoherence mechanisms and these things, like you can imagine being able to read out optomechanically, right? They don't care about light. So they won't like create quasi-particles in the same way as superconductors will. So I think just from a 10,000 foot view, it's like really interesting physics that we weren't expecting to ever be having a cross section with, but now we sort of do, and so I want to explore that. But I think potentially down the road you could have kind of a black box that just works better at the same frequency and the same temperature as a superconducting circuit processor. Yes. Great question.
While you're on that topic, I just wanted to ask, you mentioned this for nonlinearity, but I missed what line that I should be comparing that to, and I was curious.
Yeah.
How much you need to win and sort of.
Well, I didn't mention it. You just read fast.
Yeah.
So 3 hertz is at a gigahertz. So if we make a halfway, let me just explain. She was super quick, so I'll explain it. So if we use the measured nonlinearity in this waveguide system, essentially this collimated beam system, this is traveling, and we measure our group velocity, we can predict what the Kerr shift per phonon will be. And we're doing that experiment at a gigahertz. At a gigahertz, it would be 3 hertz. Now, so then you'd have to make a cavity with substantially smaller alignment than 3 hertz. Now that's pretty tough. But at 5 gigahertz, this gets better for multiple reasons. One is the wavelengths are just smaller, so larger field per phonon. But the second is that we still have this like time crunch problem here, where even our carrier concentration in our 2D electron gas is not optimal in this system. It's just really difficult to control like the distances. So 2D electron gases, you essentially like you tunnel the electrons into the quantum well. And so it's all determined by like how heavily doped these like reservoir layers are and how far away they are and the tunnel junctions between them. So it's like kind of challenging to precisely control. And we didn't get optimal carrier concentration in 2D. So if we go to 5 gigahertz and we have an optimal carrier concentration, actually this goes up to something more like megahertz. And that is like an easy cavity frequency to make. So I'll say like, so Marco Longar has some papers where they measured like SAW resonator cavities at cryogenic temperatures. They got Qs. They were I think like 100,000. So, at 5 gigahertz. So definitely way below megahertz. So I definitely think it's possible to make like low enough cavity linelets to do this stuff. But yeah, that's a great question.
Great. I think that we should probably wrap up and thank you very much.
Yeah.